That's what I thought. She was like, and then she was like, is that another camera? I was like, what brother's mom? I didn't.
It looks like there's ears.
Okay, how's everyone doing? Good afternoon. Thank you. That's nice. Hello. Today we're going to discuss coupled physics, which will become more clear, but essentially taking advantage of ANSYS and COMSOL and other softwares that allow you to cross these physical domains. And hopefully we'll have a little bit of discussion. And then we'll get into a little bit of information and some ideas about writing and expectations for the projects that you are spending time pursuing at this point. The fun thing, right, is that you haven't had a post lab for number 5, and right. That's right, there was no post lab, right? Or there was a post lab. Oh, sorry. Okay. 6. Okay, sorry. 6, there's not, right, we're on 7. Yes, okay. 6, there's no post lab, right? And then 7, also no post lab, right? So this is a time to focus on your other classes and your final project. Okay, that's what I suggest here. And yes, I need to get you some feedback on your projects as well, on your pre-proposals. Are there any questions administratively before we get into things? Suggestions, comments? I guess, I remembered something. So there was a couple of uncomfortable situations that happened with submissions, and so I sent an uncomfortable email or message as well, and I talked a little bit about it with the other class on Tuesday. Please make sure that whatever you submit is generated by the computer you are using. Okay? So, the TAs, they're very good, and we like you all, and I hope you'll still like us. Okay? But they found some things that were beyond, what we consider to be just whatever. So you know how it works, maybe some of you know how it works. It depends on how student affairs decides to do things, right? But we're not necessarily the ones that adjudicate. Sometimes they give you a thing. Sometimes there are explanations for things, and sometimes, whatever, Just please make sure that what you're submitting for the individual assignments is original work that you've done. I do not want to discourage sharing in the group meeting, okay, or between peoples. That's not what we're getting at, right? What we're getting at is you gotta have run the code, or you gotta have been running the ANSYS simulation, and that's what should go into your report. Okay, any questions on that? Okay. So thank you for your patience. Thank you for your dedication, and for your wanting to do good work. Make sure just that you don't leave any doubt about who or how it's being generated. And we'll talk a little bit about that with respect to the papers at the end, coincidentally, or maybe not coincidentally. We'll talk about the policy for generative AI. These situations do not look like generative AI, I don't think. Okay. And there were other situations that one of the TAs was talking about, and I said, I don't think, I mean, yes, maybe, but there's definitely not, it didn't seem to me that it was, I thought it was just maybe not, I didn't think it crossed the line. So there's some judgment here that we have to use. All right, so on happier notes, let's get to the coupled physics. We're going to review a little bit also later on scientific method, which we already kind of covered, so we'll breeze through that really quickly, and then we'll have a discussion on the writing for the final projects. The next preliminary outline is due for the next checkpoint, which is the preliminary outline, is Friday, a week from tomorrow, and we'll talk a little bit about what's in there. Okay, so hopefully this will be a little bit of a discussion, all right? Otherwise, it's going to be even less interesting than normal. When we have looked at this example on the left, okay, that was the turkey. The question for you to consider, for us to discuss, is were there examples of coupled physics? Okay, on the left, on the turkey. And then on the right, we had this step, okay, in a flow, in a pipe. Were there coupled physics in this example as well? All right, so let's start with the turkey. And in this case, we're talking about the turkey homework, right, that you were doing. Okay? And we were talking about how there was a temperature the oven might have been set to, and so, what are your thoughts? Were there coupled physics involved with the turkey process? Yes?
What does coupled physics mean?
Okay, that's a good question, right? So, we're talking about having to use a set of equations or trying to think about physics that would have been in one domain, okay, and did it couple to another domain? And maybe one way to think about this is your curriculum, or your curricula in MEMA. How do you split up your divisions of topics in your curriculum, in what you're studying? Have you started to do this? Have you tried to classify classes in kind of categories? Right, so what are those categories? What have you arrived at? Because our handbook doesn't actually really, there are these concentrations and there's a packaging certificate, so I guess maybe you have some ideas, right? But in terms of the subject, what are some of the categories that you kind of lump your classes into? Yes?
Thermodynamics and energy.
Right, so you've got these, so you've got kind of the thermal area, right? You've got thermodynamics, like you said. You have we have a heat transfer class that's required for the ME students at the end. We've got, energy. There's some alternative energy courses. Yeah, okay, so that's a good kind of area. We could call it thermodynamics and heat transfer. What are some other categories you can lump your classes into? Sure. Federico. Yes.
Fluids.
Right, so you've got fluids, right? We have a class of fluid dynamics. If you're in AE, there's aerodynamics. There's compressible fluid dynamics. Right? There's propulsion. So there are kind of a number of classes that you could kind of lump into the fluid category. What else? Any others? Sure.
Like chemistry and quantum mechanics, for example, mechanical properties of materials.
Okay, whoa. So I think so were you putting mechanics in a separate category as quantum, or you're linking them together?
No, like properties and like the class we all have.
Yeah. Okay. So properties of mechanics, properties of materials. Yeah. Okay. So that's more like material sciencey type area. Okay. Yeah. Okay. So that's true. That's true. It's not taught by your department, but yeah, that's true. Okay. Yeah.
Can you explain coupled physics again? I don't know.
So imagine you have a set of equations that describes forces in a solid and stresses in a solid. And you have a set of equations that use Navier-Stokes relationships for fluids. You have one class where all you do is study Navier-Stokes. You have another class where all you do is study mechanics. In the example on the right, for the flow in a pipe, how do we couple those two domains to each other? What were we calculating? Yeah, you were calculating the drag force, right? Do you remember? We asked the question in the last session. If you have this fluid between these two plates, and I'm pulling, or I have a velocity of one plate on top of the other plate, we asked the question, how do you calculate, or how do you measure the viscosity, right? And we had to think, oh, well, I've got to kind of integrate this shear stress that I have acting on the top plate to calculate a force. And that was like a rough example of a mechanics problem, okay? But that shear stress was then generated because we had a Newtonian fluid between the plates, right? And that was the mu times the dU/dy. So here, in this example, when you have the flow in a pipe, right? ANSYS was, or Fluent was so kind that all you had to do was select the step and say, tell me the drag. Right? And in reality, that you can argue is kind of some form of coupled physics. Now, it's not the super intense form of coupled physics. What would be a higher level? Sorry, if I can say. What would be a more complicated coupling between mechanics and fluids for this particular case, on the example on the right? Yes.
Like trying to test on the airfoil.
Okay, so yes, so an airfoil, yes. Now, we will do airfoils, and they're actually going to be very similar in that the airfoils that we're looking at are just going to be internal bodies around which we have flow. Okay. So it's similar, but how can we like go to the next level of coupling? Yes, Andrew. Okay, so this is, okay, so you could go to another dimension, sure, all right. That's, yeah, okay, that's not necessarily, I mean, that's increasing complexity, that's not exactly what we're going for here though, but I like it, yes.
We could, like to the next level, and then we can do, have like different types of like drags on, let's say an airfoil, like viscous drag and then pressure drag.
Okay, so we could calculate drags. Again, I'm kind of thinking, maybe I'm not asking the question right. How could you add another level of physics, another level of calculations, and another level of kind of results for this? Yes?
Like maybe we could use the drag force to calculate maybe like the shear or actually touch like the strain on the pipes.
Yeah, okay, exactly, right? It is Sam, right? No, what's your name? Matthew. Oh, okay, that was close. All right. No, not close. Your second letter is an A. That's about it. Okay, Matthew?
Yeah.
Okay, so Matthew, yeah, look, this is a solid edge all the way around. And then of course, we did different cases where we had, we played with the, with this middle boundary and an axis and said, okay, we're not going to have shear there. But what if I were just like to put a piece of rubber here, okay, in that little void, in that step? And it was a super soft rubber, and I could actually see that rubber deflect. Okay, what would I have to to do? I would have to put a mesh, right? I would have to put another set of elements there and essentially have that coupling be able to cause deflection of that material and cause there to be stresses in that solid. Okay? When we do the airfoils, like you were talking about over here in quadrant 2, I'm sorry, I don't remember your name. Yes, your name is?
Sato.
Sato? Okay, so when you do airfoils, like you were discussing, right, we try to keep it simple, but often there's enough other mess that we're trying to get to converge that we just make it a rigid internal frame, okay? But yes, people are concerned about how the air or the fluid surrounding an object is going to cause deflection. And if you think about this subject called aeroelasticity, which is essentially how does the structure of a flying airplane or vehicle get affected by airflow going past it? How does it vibrate, right? That's kind of an example, and it's tricky, right? That's kind of an example of this physical coupling, all right? Are there still questions of what we mean by coupling now? Did that make, can we kind of clarify what we were talking about with coupled physics? So going to the kind of the simpler problem with the turkey, how were physics coupled in that situation? And it's a little bit of a stretch. It's not, okay, yes, Federico.
So you had to find, I mean, you were just given a convection coefficient, but to find that convection coefficient involves it involves a whole process from like properties of the fluid. So that could be, and that's like fluids with heat transfer.
Right, right. So we came up with this H parameter, right? The coefficient of convection. Because we said, well, I'm measuring the temperature of my turkey, and it somehow is magically done at 4 hours or 4 hours and 15 minutes, okay? And for this given size, okay? And so I did this kind of experiment, and then I'm going backward and saying, okay, this is what the H has to be if the oven is set to this temperature. And that's a useful skill to do, right? In many aspects. And it's kind of going backwards. Like, oh, I would really like to be able to solve the forward problem, but in some way I've gone kind of backwards. Like, I have this result, and I got to go back and figure out what the physics were to get into that thing. And yes, there's this convection that's happening, and it's air that's flowing past the surface of the turkey at a given temperature, and it could be forced, right? You could have a convection oven where it's more forced, or it could just be the natural buoyancy of the air as it's circulating around, and as it gets to the turkey, right, the air cools down a little bit on the surface of the turkey, and maybe that makes it a little more dense, so maybe it wants to fall a little bit, okay? All right, but then it gets down, it goes down, and it gets closer to the burner again, and it comes back up, right? So you've got this kind of flow about the turkey. Okay? And for lab 7, if I can keep it straight, lab 7, you'll get to play a little bit with coupled physics. We'll have a heated wire, and you'll be able to see how the surrounding air, as it goes by it, okay, is going to be changing its temperature. And you'll be able to see how the wire set at a given temperature, how much heat it gives into the surrounding liquid as it flows by. And as you have the air going by that heated wire, okay, the rate of heat transfer, well, let me ask you, will the rate of heat transfer go up or down if you have more air flowing by an object? Assuming the air is at a given temperature which is different than whatever the solid object is. You get more heat transfer at a higher flow rate or lower heat transfer? Yes.
Higher defense?
Yeah, why is that?
More like temperature difference over time, I guess, and more molecules come into contact.
Yeah, Bobby, did you have anything you wanted to add to that?
Yeah, because of the temperature gradient, so if you wait a few later.
Right, and if the air just has to sit there and it increases in temperature, right, that gradient is not going to be as large. Yes, Federico.
Also has to do with laminar turbulent flow.
Right, so the type of flow you have past it is going to affect, and so you get to do that too. You'll get to do a laminar flow case, although the heat, yeah, we'll do laminar flow, and we'll also do turbulent flow. And it turns out at the small numbers that we're playing with, it's not going to make a huge difference for this particular case. But you're absolutely right; it can make a difference. Okay, good. So we can have coupled physics through a force, okay? And it could be literal forces in a mechanical sense, or they could be forces like heat fluxes or pressures. At this point, you've also seen that when we solve this kind of K matrix, or we have a K matrix times some parameter we're interested in, we said that's equal to an F matrix, right? So that F, right, could be coupling between two domains. You can have coupling because of geometry. All right, so this is kind of related to what we were talking about. What if that fluid flow causes the step itself to mechanically deform? It's a rubbery step. Okay? And so that change in geometry can cause there to be a change in the flow, right? So we're starting, we'll talk about the difference between one-way coupling and two-way coupling in just a second, but you can get an idea that simulations that change the geometry are going to affect other physics that we might be simulating as well. And then you can also have coupling in terms of changing the properties of the materials that are involved. And we'll talk a little bit about this. So you can imagine that temperature can affect a lot of these things. Right? Elastic modulus included. You have the glass transition temperature of many polymers, and so that's kind of the temperature at which it goes from a solid-like state to something that's a little more liquid. And then to couple or not to couple, that is the question. All right, whether it's null or in the mind, to suffer the slings and arrows of outrageous fortune, or to take up arms against a sea of troubles. So, if we're going to couple, we want to kind of make sure that that additional complexity is worth it, like we actually care about. So, in this area of soft robotics, I've shown you a little bit of what we've done, and this paper robotic thingy that we inflated. You can get the idea, right, that as you decrease the elasticity of the solids that are surrounding your liquids, air, for example, the coupling becomes more important. And so we get ourselves into kind of tricky situations with this whole area of soft matter. As the forces that we have in one domain, they end up affecting geometry or affecting the physics in another domain. And often we want to, over-design a little bit. We want to make sure that our structures are so strong that we don't have this issue. Now, there's one-way coupling and two-way coupling. Any ideas what the difference would be? I think some of you may have already thought about this. Okay, what do you think the difference between one-way coupling might be and two-way coupling? And maybe quadrant 2. Yeah, got some head nods in the positive direction. Okay, what are y'all thinking? What would be the difference between one-way coupling and two-way coupling? Yes.
The shear stresses.
Okay, yeah, so that's okay, so could you give me a little more detail on that? Okay, I can see it. Just can you talk about what that would, what do you mean? Is that, in your mind, is that a one-way coupling or a two-way coupling? And I mean, what shear stresses are you thinking about?
Like, you're coupling it like one way. You're only gonna have shear in one direction when it's like one.
Okay, okay, all right, yeah, all right, okay. Yeah, okay, so you could say that I've calculated what the force on this object is, and that force doesn't lead to a change in the geometry of the step. Okay? And since it doesn't lead to a change in the geometry of the step, and it doesn't lead to a change in the friction or whatever you have as the liquid's going on, it doesn't lead to a change in the no slip condition that we want. Right? There's no like interesting slip line mechanics or anything going on at the liquid solid interface. We could say that's a one-way coupling. Okay? So like we know that it's going to exert a force on this object, but it's not going to change the fluid flow. Okay? Is that that's exactly what you were thinking, right? Okay, maybe, or something like that, right? What's your name? Yeah, all right, yeah. All right, so what would be an example of two-way coupling? If that's an example of one-way coupling, what would be an example of two-way coupling? Yes, Frank?
The example of like the rubber part, where if the fluid deflects the rubber, and then because the tube is changing shape, the fluid will move through the pipe differently, so they're both like interacting with each other.
Right, exactly, right? So we have like a soft tube, and we've got flow going through it, or there's a step or something, and now we've expanded it a little bit. And so now that means that if I have my continuity, at least for one, right, my V1A1 equals V2A2, right, and I'm going to start to see, ooh, something's got to give. Like my flow rate might go down a little bit, or my velocity might go down a little bit, all right, because I've got a bigger cross-sectional area. And so it can go cyclic. So you go, oh, well now I changed that. Now I got to go back and figure out what the new forces are on my rubbery material. And so it goes back and forth. And these types of problems can get very complicated very quickly. So typically we want to avoid two-way coupling if we can. All right. If your simulation is like, okay, just one way, that's going to be a little bit happier. But fluid structure interactions, there are many cases where you have them working with each other, and that's complicated. Fish, right? That's a complicated one, right? Because you have the muscles and you have the fluid flow going past it, and then that then affects the geometry of the fish. Okay, and then you've got to like balance this thing back and forth. Okay. Now, here is a fun, well, this is Professor Singer, all right? Well, it's not Professor Singer, but this is something that he's done. Okay. And this is just an opportunity for us to discuss how these physics might couple with each other. And was it one-way coupling, is it two-way coupling? And we could discuss that in some cases, but the idea is we have a thermal system. We start on the column on the left, and we think about how do thermal physics affect other thermal physics? How do they affect fluids? How do they affect solids? How does it affect even electromagnetics? Okay, and we keep going through this whole thing. And this matrix is not 100% symmetric, okay? Because you could have, we could have thermal affecting fluids in ways that fluid affects thermal, or does not affect the thermal system. Did I say that right? Thermal affecting fluid could be different than fluid affecting thermal. Okay. So let's go through this exercise a little bit. How could a thermal system affect itself? How could we have coupling effects? And maybe I'll get us started here. Okay. So in this case, it could be that the properties like conductivity and heat capacity would be dependent on temperature. Okay? You got that idea? For sure, I mean, there's phase change that can happen. All right, so water going from solid to, well, that's more of a solid part, the thermal solid coupling, right? But the conductivity of a material is often dependent on its temperature, as is its heat capacity. Okay. All right, now how could thermal physics affect fluid mechanics? This one is probably a little bit more straightforward, or in some ways is straightforward. Yes.
It can affect the flow, like having more viscous fluid, even at a higher temperature would make it less viscous.
Yes. So viscosity. Very good. Very good. Okay. What else? Yes. Oh, yes. Thank you. Okay. So yes. Now do you have something to opine, Bobby? We're thinking about how thermal physics can affect fluid mechanics.
Well, yeah, I mean, material properties change. Big one.
Yeah.
There's convection, so heat causing fluid motion.
Yeah, exactly. Those are good, right? So we have our properties, okay? We can have expansion as well, okay, of the fluid. And yeah, you can have induced convection. I like that. So let's add that too, right? You can induce flow. Okay. How can a thermal system affect a solid system? Yes. Sure. So let's say it can affect the elasticity quite a bit. All right. We'll say that, and it's kind of similar to what we have here. We can say that if that bar is constrained between two walls and it expands, we can have a significant amount of stress induced. Remember these problems for mechanics? Okay. All right. And what about electromagnetics? This one I think is a little bit of a stretch for us mechanical engineers. Oh, okay, what's that?
Resistivity.
Okay, so resistivity, sure. We could put that down. That's possible. Okay, so we're going to say resistivity could be affected. That's not density. That's resistivity, as you put it. Okay. You could also have a change in the permittivity. So that's like permittivity is what we think of when we have our capacitors and capacitance, like dielectric properties, and also you can have resistivity, which is affecting the resistance. The resistance. Okay, good. How can we have fluid? Let's go over here. Fluid thermocoupling. Okay. Well, we can have the transport of hot or cold materials in a thermal system, so that would be the heat transfer. And if you increase the flow rate, right, you're going to get more convection. We talked about this a little bit before. And we talked also about how thermal can introduce flow, right? And this is a nice example where you can have kind of two-way coupling as well, right? So you can have one affecting, say, the fluid properties. You can have heat affecting it. And because it affects the fluid properties, then it's going to potentially go back and affect the thermal properties as well. Fluid-fluid interactions. So you could have different physics interfaces. So gas is a fluid, as is liquid is a fluid. And there are different ways of handling these. We're not going to discuss the phase field methods and the volume of fluid methods, but there are essentially ways that you will, or we would say, this material, like I draw a border, and like this, let's say I have something like this. This is a border, and this is gas. Oops. And this is going to be liquid. All right. And so down here, you say, okay, this at this location, we'll call it Y, is 1. And that means it's 100% liquid. And here you say the phase at this location is 0, which means it's 0% liquid and 100% gas. All right, and so these kind of phase field methods, they actually, at the interface, it gets a little bit tricky. Right? And as you get close, there's like some diffusion that happens, and like you're like, oh, it's half and half. That's not really how it works, okay, but that's how it gets modeled. Fluid, solid. Okay, we already talked about this a little bit. Talked about the stresses that can be induced on a solid material because you have fluid mechanics involved. Aerodynamics, hydrodynamics. Okay, and then you can also have fluid coupling to electromagnetics. So you could have a fluid that has different electrical properties, and as you induce flow on that fluid with different electrical properties, it changes the electrical nature of the system. And we'll talk about the other coupling where you have electromagnetics that couple into fluids in just a minute. But that's one way that fluids can affect electromagnetics. All right, what about how could solids affect thermal systems? How could solid mechanics affect thermal systems, thermal physics? Yes?
Collisions.
Collisions, yeah, all right. What happens in collisions?
Energy is released.
Yeah, you could have a lot of energy released, right? As an object runs into another one. You could have heat released, right? We're talking here, this is thermal. If you have friction between two surfaces as well, right? So if you have rubbing between them, that's another way you could have heat release. If you do some sanding or something like that too. So yeah, there can be forces due to friction, the geometry or the configurations. We'll even say that you can have, I like that, you have dissipated heat in collisions. Okay, so solid fluids, you could have a system with pistons in it, for example, where you're displacing the fluid, you're reducing a pressure, inducing a flow. Also, I guess you can even think of just changing the geometry of the pipe. As you change the geometry of the pipe, you're going to be affecting the flow that you have. And this can be coupled, all right, two-way, all right. You could have solid fluid and fluid solid. interactions, right? And this whole area of like FSI, right? Fluid structure interactions, that's still kind of a pretty, it's a very important and interesting area, right? If everything from, like we said, fixed wing aircrafts, aeroelasticity, to being able to look at how the turbines and the blades on these turbines are going to be affected by the flows that you have, and whether or not they're going to break. So, solid, yeah. You have stresses, you have forces. Essentially, this is like the solid mechanics squared, right? And solid electromagnetics. I'll just say that as you move your magnets around, or as you move your conductors around, you're going to be coupling into the electromagnetic properties. And your phones, right? The geometry of antennas matters quite a bit. Okay? And there have been quite a few advances over the past few decades in this as well. And we've gone, to the miniaturization of our phones that we can hold in our hands. Okay, electromagnetics. So, anyone enjoy inductive eating at home? Maybe? No? Should I go in? I read an article. We have gas in our house for the stove, but anyone? The people, I was reading an article recently. It's just a news article, but this is a thing, right? Because you can get the heat in. It's like 80% efficient or something. It's quite efficient to use induction to get heating of your pots and pans. And then you have electromagnetics that affects fluids. So this also used to be a big area. It's still a big area for anyone who's working in it. Okay. But is anyone doing research in magnetorheological fluids or electrorheological fluids? A lot of people were doing this at some point. So they put like little steel beads, for example, in a fluid. And then you could have like a magnet that would like make it really solid. Okay. Or like, change the configuration. Not beads, but it's like those, like little, or the magnetic ferrite, the magnetic stuff in there. You can see like the little jagged edges, right? It looks all fuzzy and stuff. And you also have kind of similar things with electrolytical fluids as well, where it responds to the electric field and it changes viscosity. Okay. Motors, electric motors. That's a huge advance, right? Where you have the Lorentz force, and you have back EMF, right? The electromotive force going backwards, and so we have these extremely efficient electric motors. And finally, you can polarize or magnetize systems by using high electromagnetic fields. All right. We did it. Good. So now, back to that question, what do we mean by coupled physics? Well, these are the domains that you'll probably be working in. Okay? Someone did mention quantum, all right? But these are the domains you'll probably be working in, maybe in this class, maybe not in this class, and these are different ways that things can couple with each other. Okay. So, in the lab, you'll have an opportunity to kind of do your first physics problem where you're seeing how the temperature affects flow. You get to natural convection, where the fluid is heated, and that will lead to a change in density because it uses the ideal gas model, and that causes buoyancy to induce flow. Right, so that'll be fun, amongst other things. Now let's talk a little bit about your projects. So, as engineers, sometimes we have to think like scientists. Okay? And often when we are working on research projects, we are attempting to use the scientific method. And we already talked about this a little bit at the beginning of the class. And we bring it up again because this is relevant to what we're trying to do in the final projects, in the assignments. Okay? So we're working on creating a hypothesis. Now you can have your area of interest. You may even have some observations. You may even look at what other people have concluded. We want you to kind of come up with a hypothesis. And what is, I think I said it in this class, what is the word that you use when you're thinking about, do you have a hypothesis or not? Okay, maybe not. What do you think a hypothesis is? Like, how would you form one? Yes, Bobby. Okay, so if then, that's true, right? So if something, then, okay, other ideas? If it's raining outside, I hypothesize then I would probably get wet when I walk outside. Right? So there are some, as people say, throwaway hypotheses. Right? Although we can say there's no such thing as a bad question, but there could be something as such as a bad hypothesis. Yes. Okay? But we try to be we try not to be subjective. We try to be very objective in this. Because we got to think like science. What are other things that you think about when you're putting together hypotheses? Yes, Andrew. It's testable. Okay, good. Right? So it needs to be testable. And can you tell me something about what it means to test a hypothesis? Right. Now, is it easier to prove or disprove a hypothesis? It's very easy to disprove a hypothesis. You just need one solid, concrete counterexample, and then you knock it off. It's very hard to prove a hypothesis, though. Right? I mean, we do get to the point of having theories, which essentially are hypotheses that have been tested over and over again, and we haven't yet found too many examples that disprove it. Okay? And so Newtonian mechanics stands pretty strongly for most of the things we're going to do in this class. Or pretty much everything we're going to do in this class, right? But we do know that it does break down, okay, at high speeds, right? And so there are certain situations where relativity comes into play, and there are other situations that are very, very small where quantum has to come into play, right? And people are trying to find this universal theory of physicists, right? But there are people that do that still seriously test Newton's laws or different things like gravity, okay? And it's like, we just got to show that it doesn't work one time. Okay? The word that I like to see in a hypothesis, now does this sound familiar? Depends. Okay. Did I not say, maybe I said it in the other class, but not this one. Did I talk about depends here? No? Okay. So if you are thinking about, something like structures, for example, right? The weight that this desk will be able to handle depends on the yield strength of the material that's used. Okay? Right? That's a hypothesis. Okay? And it's nice to not have it be yes or no. Okay? To say that something more like it depends, but it also varies, or it will increase the weight that it and of this weight that this table can withstand depends on the yield strength of the material used in this table, and will increase proportionally to the yield strength, or something of that nature. Okay? So depends is another way to come up with a hypothesis. You all get to test and put out hypotheses for your projects. Okay? So you are going to make sure that in your paper you say the hypothesis is blah blah blah. That the coefficient of drag will increase with the angle of attack, or something of that nature. Okay? The heat transfer, okay, the cooling of my processor is going to increase as I increase flow. Okay? The hypothesis is this. Now, you need to test it, right? Which means that you're going to vary a parameter to test your hypothesis. Now, we don't want it to be a throwaway hypothesis, and I don't expect that you necessarily are going to be so scientific that you don't go back and reshape your hypothesis a little bit, okay? Based on the results that you get. Nonetheless, we want you to put forth a hypothesis. Okay? Any questions on hypothesis? Now, I think we talked a little bit about the different types of studies and how experimentalists and theorists, they work together and how they help each other. Okay? We also might have talked a little bit about the pros and cons of analytical solutions. And what we want to talk about now is the writing, okay, for the final projects. And you're like, no, this is not XPOS. Well, it is not XPOS, right? There are ways, though, for us engineers and scientists to construct what we say, construct what we write in an almost formulaic manner that others can understand. Okay? And I'll show you one approach to doing this. Okay? So, before we do that though, when you write, we have to know our audience. Who is the audience for this class?
You.
Okay, we'll say yes, all right? So you can have your teacher or TAs, okay, being the audience, all right? What other types of audiences might you have? Maybe not in the context of this class. Yes?
Like peers or people we're working with.
Yeah, you got peers, right? And we'll even say bosses. Okay? It's kind of important. Yeah, what are you going to say?
You have to maybe the general public.
Yeah, so you got general public. Okay? Now, these people can be stakeholders as well, right? If you create a wonderful invention or discover something that's extremely valuable, they can benefit from this quite a bit. Just as your boss could be a stakeholder, and even your peers could be stakeholders. You could be putting it before program managers or funding agencies, right? Or venture capitalists, right? Right? There's a number of types of people you could be selling things to, right? Or you could be J.K. Rowling, right? And you could be selling it to kids and parents. I can now say that I've listened or read all the Harry Potter books. I couldn't say that a couple weeks ago. Right? So there you go. But you have the opportunity to sell, right? Where it's about, we had to sell ideas. Okay? And now you've also got social media, right? You've got all kinds of audiences. Now, some of these people have no patience for a written report, okay? Or no patience for YouTube videos that are an hour and 20 minutes long, right? But you can try to think about how we want to involve people, how to get them to at least understand what we're trying to get across. And what types of genres? Well, for our purposes, we have reports. We have papers. And these can come in all kinds of varieties. So journal articles, these are typically longish. And then you have short communications that are typically short. Okay? So Professor Singer has designed this class so that what you write would be something more akin to a short communication. Let's talk about what we care about. Grades. Some of us care about it, some of us don't. Some of us don't like it. Me too. Okay. This group project final paper is worth 23%. Okay, and you already got something, you're already doing this, yes, yes. And the group project checkpoints are worth 17%. The final project video is worth 5%. Okay? And so how much is the final project worth? What percentage of your grade in this class? 45%. Okay? That is a lot. Okay? The project checkpoints that we have, they're worth 17%. The peers in this case are just your other teammates. Okay, we're not going to do it's not going to be like, the peers are just your teammates, right? What questions do you have? Since it's worth this much of your grade, what questions do you have about getting this right? Yes?
We thought to have only 2 people.
So I'm going to go through the things. The goal is not to have only 2 people. Okay, that's the goal. So we'll see how it shakes out. All right. Good question though. Other questions? Yes, Bobby.
Is technically accomplishing what we set out to try to simulate the thing that decides our grade?
We'll get into that in more detail. You need to have a problem that you can manipulate parameters. Okay? So, yes, in a sense, you need to pick a problem or scale back your problem such that you can get an output for an input. Right? So, let's just say that you started off wanting to do the simulation of a flapping wing on a bird. If anyone's doing that, I will kindly say this is too difficult for this course, okay? But maybe you could say, I'm interested in attempting to simulate the 2D profile of something that looks kind of like a bird wing while it's gliding under steady state flow. right? That could be something that you do. And then you're like, okay, I could kind of do drag and coefficients. Drag and lift coefficients. Okay? And I hope it will converge. Right? That's the other thing. That's like within kind of a realm. And so then I'm going to change the parameters a little bit. And maybe I will change the chord length a little bit. Okay. Or I'll change the, I'll add a bulge or something. This kind of stuff is actually quite hard to do, right? And so that would kind of be maybe one example. But that's, even getting that problem to work is on the harder end. You do need something, and you need to be able to test your hypothesis, right? This is you have to have a hypothesis that you can test. In order to test it, you have to vary the parameters that you put in. Other questions you might have at this point? Yes?
Is it too late to add something to the proposal or the project?
No, it's not too late. It's never too late if you care enough. All right, so no, in fact it isn't. So you can be changing things until the final paper is due. Okay?
Like,
I don't advise, I hope we'll get to an agreement though before that. Yeah.
I was thinking, like you were talking about coupled systems, and I was thinking maybe I could add a coupled system to, like, or to encompass two different, like, sort of topics into our simulation, into like our project.
Yeah.
And we could do that.
Yeah, you can do that. Just, I highly suggest it be one-way coupled. Okay, not two-way coupling. Typically, two-way coupling is going to be very hard.
Okay.
Okay.
I can talk to you about that.
Yeah, we can talk about it. And then we have office hours and we can talk about this. Okay. What about the final project video? Any ideas on that? Okay. Have you done videos for any of your other classes at this point? You have? Which class?
Statics.
Statics, okay, all right, great. Good, good. Okay, so last time I taught, we did presentations. The class is too big for that, all right? And we did videos. So the 2-minute kind of promotional video, we'll call it. And I think I have to show you a video at some point, okay? I'll have to show you some examples. This can be kind of comical, it can be kind of fun. It could be a collection of things with appropriate citations. We'll talk about that a little bit. Okay, that demonstrates the importance. So let's say that you want to do flying birds, right? So you find some videos. Or you have people dress up as birds and you show them flying around, whatever you want to do, but you explain just how important for their survival and for whatever the flying bird is. And then you spend 2 minutes talking about, that's 2 minutes of that. And then you spend 2 minutes, so that's more creative, more fun, selling your idea. And then you spend 2 minutes essentially PowerPoint. Okay, maybe not PowerPoint, that doesn't sound right, but in some way, it could be, you could do math, whatever you want to do, but that's where you explain the hypothesis and you explain the results. And that, I suggest you use probably some form of slides. Does that help clarify maybe kind of what we're getting at? You all can create videos better than I can at this point. I'm just amazed at how you do that. Okay. So, I guess actually this is maybe has anyone started putting their insights up on Canvas in here for the guest lectures? Okay, you're supposed to watch 4 of them. There are about 7 of them. Okay, you get to pick 4 and enjoy and write another. Okay? All right. Now, each project will need some kind of study with a testable and specific hypothesis. Okay? The complexity of the simulation is not a requirement, but the scope of the simulation needs to be enough to fuel a reasonably in-depth discussion. Groups of 3, okay, should permit complementary simulations for a systems level perspective, or not, I'll say, or not. You could get into something that's so complicated that you're just like, I just want to get it to work. Okay? So that's maybe, the third one's a little bit off. We need to think about discovery, hypothesis, results, analysis, and discussion. All right? And this is the guide that Professor Stingler has put out for us in terms of where he thinks the sweet spot might be. Okay. Now, and these are some topic examples. All right? So falling glider, that's not too dissimilar from the bird we talked about. There seems to be a lot of examples out there now, simulation examples for balls. Okay, heat sink, fluid mixing. Yeah, okay, do laminar. That's not so bad. Internal pipe flows. Okay. A falling drum leg. Okay, so that's something you could do. Airfoils, a lot of people do them, and also fluid structure interactions. Okay. Now, this is from my postdoc advisor, and he wrote a paper, actually titled "Writing a Paper." And what I like about it are multiple things, and I'm not perfect in following everything that's out here, and he'll tell you himself that this is kind of an idiosyncratic approach to writing. Okay, but it's a very short read, and I think it's worth your time. And this is how, quite frankly, that research group of 30 people got things done. Okay, we had a process, and this is kind of how it works. And so you are attempting to tell a story, and you're attempting in the outline process to save yourself time. If you can come up with the story before you do all the work, you can kind of hopefully do fewer experiments and prove or disprove your hypothesis. You may have to revise your hypothesis, but the idea is that you try not to just test every little thing in the world and then go through the data and figure out what in the world you have to tell. Okay? Now, some people do that kind of research. That's fine. Okay? This is more about storytelling. So, there are kind of multiple sections, but the introduction is often the hardest to write. Okay? It's kind of like you gotta sell what you're doing. Results and discussion, actually, the results often are the easiest to present. Okay? And the discussion can be interesting, can be hard, right? But it's going to be in there. And then the conclusions, what does it all mean? All right? Now, for this assignment that's due a week from tomorrow, we want an outline that has introduction, results, and discussion. Results and discussion are actually going to be one section in this way. I think Professor Singer had them separate. I think it's fine to put results and discussion in one section together. You want to discuss a baby step benchmark. You want to have some paragraph on the geometry we'll try to simulate, and then you want to have some type of sketch or CAD, and that's pretty much it besides the peer review. Now, what we're saying is, in the outline, you need introduction, results, and discussion. So this is what the outline for the final paper will be. So what I'm asking you to do is to outline this and that. It's not done. You can hypothesize what it should be for a week from tomorrow. Okay, but just bullet points. Hit these bullet points. This is the problem I'm trying to solve. This is what we plan to do. This is why we're doing it. This is who else has done what. And then the results, this is how you're going to check for convergence. These are the types of images we expect. These are the data, and these are the explanations, right? So that's what we want in a week. Now, the layout for the final paper has a huge, or the rubric for the final paper has a huge emphasis on getting this right. Professor Singer would put 10 points for discussion and 3 points for results. Okay? So we need to have variables that we're tweaking and then discuss what that means. Now, references are extremely important. And I gotta do this extremely fast. I highly suggest that you use Zotero. Highly, okay? And I highly suggest that you look at the Zotero folder that's already been created, okay? So there's this folder that you can join in the cloud, all right? And please don't, oops, this is, yeah, here we go. So you create an account, and I suggest you search for this. This is 439 Multiphysics, all right? And these are people, only a few things have ever been added to it, okay? But what Zotero allows you to do, as you find a web page, as you find whatever you look, whatever you want, you can have it automatically import the information into your library. Uh-oh, this may be, okay, this is not too embarrassing. Okay, let's do, sorry, let's just, I'll close my library. Okay, and, all right, so here's the 439, okay, Multiphysics, all right? And this is funny. Okay, some people actually use this not appropriately. This is research stuff. All right, anyway, so what you can do, let's say that you're a group, awesome. Okay, and let's say that you're looking at scholar.google, and you are interested in, well, that's what I'm interested in, elastomeric airfoils. And let's say that these people are really nice and cool, all right? And you want to bring this into your awesome folder. All you have to do once you've installed the extender is hit this button, and it saves it to awesome. All right, and there's a bunch of different things there too. Okay, so now it's in the awesome folder, and we can all share this awesome folder, or you can make subfolders, whatever you want. And now you're in the middle of your Word document, and I highly suggest you use Word. I know you all use Google. That's okay. Okay, but let's say that you want to do something awesome, right? Elastomeric airfoils are awesome. So then what do? You go ahead and you click on Zotero, you add a citation. IEEE is a good format. And let's say elastomeric airfoil. Okay, group literature, 439 Multiphysics. All right, enter, there it goes. That's all you have to do. And you say, hey, I want the bibliography. And then you say, add the bibliography. Boom, there it is. Okay? And then it keeps track of it for you. I highly suggest you use this. Okay? And our policy has changed a little bit in terms of what we expect for the generative AI. Okay? The basic idea is if it's something that I don't consider to be general knowledge, please include a reference. Okay. That's what you got to do. And we'll check the references and make sure that they exist. As you know, generative AI sometimes needs references. It's getting better, so that's all. Okay, any questions on the project? Yes, Olivia.
Are you going to give this together proposal before this is due so that we can apply it?
I'm going to try. try. Okay, so that means this weekend. Like Monday would be the earliest. Okay. Thank you, Olivia. All right. Any other questions? All right. Thank you for your time. Let's go ahead and switch over to the attendance, and we have an announcement from one of our peers here. Let me just get this over. No, I did the. Is that right? Yes, it's right. Okay. Actually, I don't know if you want a picture of yourself in everyone's thing, huh? Maybe you can do. Oh no, you can do. You can maybe do it from over here.
Okay. Yeah. So let's. Okay. So you guys might not have heard, but Pi Tau Sigma, which is the Mechanical Engineering Honor Society, is partnering with ASME. Speak louder? Okay. So Pi Tau Sigma, the Mechanical Engineers Honor Society, is partnering with ASME to host the first annual MAE exclusive networking event. So it's just mechanical and aerospace engineers. The social event will take place next Wednesday in the multi-purpose room in Bush Student Center. And so that's Wednesday, March 12th. So you still have time to sign up. And there will be recruiters and engineers from companies such as Valcor, the Naval Nuclear Laboratory, Princeton Plasma Physics Laboratory, and they will be hosting 2 networking cabling sessions, one in the morning from 10:30 to 12:30, so 10:30 a.m. to noon, and the second from 2:30 to 4:30 p.m. And then there's also a panel event which will feature engineers from companies such as Pratt & Whitney and Siemens. And the panelists will be answering questions and giving advice and providing insights for young professionals entering the industry, such as all of us. This is a great event and a wonderful opportunity for all of you because you don't have to go to Livingston. It's right here in Bush. It's in the Student Center. It's easy. It's next Wednesday. It's free. So sign up. And I have a QR code right here, which you might actually be able to scan even from that distance. You can attempt to scan.
Whoa, this is amazing. Does it work?
Yeah.
It worked? All right. Great. Okay. Thank you very much, everybody. Yeah, good announcement.